Hi class, in this video what I want to do is I want to talk about applications of integration, and specifically I want to talk about work. So this is kind of like a physics example for you for how you would use your calculus. Okay, so we have two objectives in this lecture. We want to find work done by a constant force, and we want to find work done by what's called a variable force. Okay, so let's start with work done by a constant force. This is pretty straightforward and easy actually. So in general, work is done by a force when it moves an object. So like when you push an object or pull an object, okay? If the force applied to the object is constant, then the definition of work is very simple as follows, okay? So if an object is moved a distance d, 5 feet, 1 mile, 2 inches, whatever, any distance, in the direction of the applied constant force, so the force will be some value F, then the work that we denote as W done by the force is defined as the work is equal to force times distance. Okay, so work is always the force applied times the distance. Just remember that because that'll come up throughout this lecture a lot. Work is equal to force times distance. All right, so there are four fundamental types of forces, right? Gravitational, electromagnetic, strong nuclear, and weak nuclear. So a force can be thought as a push as a pull, as I said. So a force changes the state of rest or state of motion of a body. So when you apply force to it, it changes the state. So for gravitational forces on Earth, it is common to use units of measure corresponding to the weight of an object. So let's talk about that, the weight of an object to determine force. Let's determine the work done in lifting a 50-pound object 4 feet. Okay, so here's the visual of it. I have this 50-pound object and I'm pulling it up 4 feet. So the magnitude of the required force F, all right, is the weight of the object as shown in this figure, so 50 pounds. So the work done is lifting the object 4 feet. So work is equal to force times distance, right? So going back, force times distance. So the force, 50 pounds, times the distance, 4 feet. So we would say the work done is 200 foot-pounds. Okay, that's how we define it, 200 foot-pounds. So in the U.S. measurement system, work is typically expressed in foot-pounds, inch-pounds, or foot-tons. However, in the international system of unit, excuse me, the basic unit of force is the Newton, right? You've probably heard of that in your physics class. So the force required to produce an acceleration of 1 meter per second on a mass of 1 kilogram, right? In this system, work is typically expressed in Newton meters, but we also call this joules. All right, in another system, okay, it's the centimeter per gram per second, the CGS system. The basic unit of force is a dyne. All right, so this is the force required to produce an acceleration of 1 centimeter per second on a mass of 1 gram. All right, in this system, work is typically expressed in centimeters, also called ergs, or in joules, but we'll mostly do it in joules. All right, so I have this table here that summarizes the units of measure. I won't go through it all, but you should just have this handy when you work the problems. All right, so now we want to get into the calculus of all this. All right, and this is work done by a variable force, and because sometimes the force being applied isn't constant. We're going to need to talk about the rate of change, and this is where calculus comes into these type of problems. All right, so when a variable force is applied to an object, calculus needs to determine the work done. All right, this is because the amount of force changes as the object changes position. So think about like a spring. Okay, so you have this long spring, and you're going to compress the spring. So when the spring is really spread out and easy, it doesn't take much force to push the spring together. But then as you push and push the spring towards its center, push it in on itself, the spring compresses and it gets more resistance, so it requires more force to push it. All right, so I'm going to walk you through how this is set up, the theory behind it. So consider an object that is moved along a straight line. So a straight line from x is equal to a to x is equal to b. All right, and this is by a continuing varying force. So the varying force is going to be measured by a function, right? So, where the object is along the position is determining how much force we have. So we're going to denote the amount of force, the varying force, f of x, some function here. All right, and we're going to let delta be a partition that divides the interval a to b into n subintervals determined by the following. And what you're seeing here is basically we're going to set up a Riemann sum, okay? So we're going to let delta xi equals xi minus x sub I minus 1, all right, for each xi. And what we're going to do is we're going to choose some ci such that it falls between the interval, all right, of those xi's, okay? Then at that ci, we can denote the force as f sub c sub I, f of c sub I, excuse me. Because f is continuous, you can approximate the work done by moving the object through the ith subinterval by this increment. So delta work, right, the change in work here is equal to f with that c sub I times the delta x sub I, so the incremental change in x. So as shown here in this figure here, the amount of force changes as an object moves this delta x. So the total work done as the object moves from x is equal to a to x is equal to b is approximately this. So the work is the sum of the incremental work done on these intervals. Okay, so the first interval to the nth interval. Okay, so we're going to replace the work, all right? Remember, work is defined as the force times the distance. So we approximate the distance approximate the force by using the function for the force evaluated at that c sub I in the interval times the distance, right? The distance is delta xi. All right, so now you can see what happens, right? This is how we've been setting up the integral in this class, or in Calc 1 and in Calc 2. So what we're going to do then, this approximation becomes better and better as, you know, the length of the largest interval goes to 0, or as the number of intervals goes to infinity. So the work done here you can just see is a Riemann sum. So the work done is equal to the integral from a to b of the force function with respect to x. That's it right there. All right, so the definition here, if an object is moved along a straight line by a continuous varying force, and we have a function that defines the force, then the work done by the force as the object is moved from x is equal to a to b is given by the integral from a to b of the force function with respect to x. That's it. All right, so the following 3 laws of physics were developed, okay, and we're going to talk about how you use them. Okay, so the first is Hooke's law, and it's the force required to compress or stretch a string, all right, within its elastic limits, right? You can't compress a string in, you know, further than it's possible, or expand it and it'll break, is proportional to the distance d that the spring is compressed or stretched from its original length. That is, the force is equal to some k times d. All right, d is going to be that distance that the spring is compressed or stretched. And this is where the constant of proportionality k, okay, this is the spring constant, and each spring constant is different because it depends on the specific nature of the spring. Okay, so when you're going to stretch or compress a spring, okay, the force required is the constant of proportionality times the distance. And we'll do a problem with this. So we have Newton's law of universal gravitation. The force F of attraction between two particles of masses m1 and m2 is proportional to the product of the masses and inversely proportional to the square of the distance between the two particles. Okay, that is the force of attraction between two particles of different masses. Okay, this is where m1, the masses are in kilograms, and d, the distance, is in meters. All right, F, the force, will be in newtons for a value of, if you take this g, so the force is equal to g, which is equal to 6.67 times 10 to the negative 11 cubic meters per kilogram squared, per kilogram second squared. All right, g is this gravitational constant, right? You take m1 times n2, you divide it by the distance squared. All right, this next law, the force between two charges, okay, and those charges are going to be defined as Q1 and Q2 in a vacuum, is proportional to the product of the charges and inversely proportional to the square of the distance. Okay, it kind of looks like the same Newton's law in the previous slide. The distance d between the two charges, that is the force, is equal to k, okay, times the division of Q1 times Q2 divided by the distance squared. Okay, so Q1 and Q2 are given in electrostatic units, and the distance is in centimeters. F will be in dynes, all right, for a value of k is equal to 1 when we do these problems, if you have those conditions. All right, let's do a problem now. Okay, so this is about compressing a spring. So even before I read the problem, compressing a spring, that tells us we're going to use this law right here, okay? So it's important to recognize when you're doing a problem how to do this. So the force is equal to K times the distance. All right, so a force of 30 newtons compresses a spring 0.3 meters from its natural length of 1.5 centimeters, okay? Find the work done, okay? So remember, work, all right? I want to find the work done. I'm going to go back. The work done, so I'm going to integrate from a to b of the force function d of x. Well, with a spring, this is the force function, okay? So find the work done in compressing the spring an additional 0.3 meters. All right, let's work through this. All right, so by that law, the force f of x required to compress the spring x units from its natural length is f of x is equal to k times x. So what we need to do is we need to find this k, okay? So because, all right, we're saying a force of 30 newtons compresses a spring 0.3 meters. So the force, if I push it 0.3 meters, okay, it requires 30 newtons. All right, so it follows then that 30 must be equal to the x here, because I'm changing the distance 0.3 times k. Okay, so I'm solving here for that constant k. So if I divide by 0.3, it's telling me this constant of proportionality, okay, for the spring, k is equal to 100. So what we're seeing here is the force function f of x is equal to 100 times x, and you can see this here. All right, so here's my spring. To move it from its original position, 0.3, okay, it requires 30 joules, or 30 newtons, excuse me, sorry about that, 30 newtons. So seeing that, I can figure out what k was, which is 100. All right, so to find the increment of work, assume the force required to compress the spring over a small increment, delta x, is nearly constant. So for very, very small x, that's pretty straightforward to assume. So the increment of work is delta w, which is force times the distance increment. So the force, we know the force function was k times x, or 100x times delta x. All right, so because the spring is compressed from x is equal to 0.3 to x is equal to 0.6 meters, less than its natural length, okay, going back, find the work done in compressing the spring an additional 0.3. So I've already gone, this is how I'm getting these values. I've already gone 0.3. I want to go an additional 0.3 to get me to 0.6. So work done is the integral from a to b of the force function dx. So we're going from 0.3 to 0.6. My force function is 100x dx. Well, when I integrate 100x, that just becomes 50x squared. And we're evaluating that from 0.3 to 0.6. So, you all know how to do that, plugging that in. So you end up just getting 18 minus 4.5. So the force required to do this would be 13.5 joules. All right, so note that you do not integrate here from x is equal to 0 to x is equal to 0.6 because you are asked to determine the work done in compressing the spring an additional 0.3 meters, not including the first 0.3. Okay. All right, so let's just talk about this in a little bit, summing this. So the summation of increments in the form delta W, okay, so the additional work or the change in work is force times the distance increment, which is equal to the force function times delta x. Another way to formulate the increment of work, okay, is delta x is equal to the force increment times the distance instead. So delta f is equal times x. So the second interpretation of delta W is useful in problems involving the movement of non-rigid substances, okay, such as fluids and chains, okay. So let's do an example when we're talking about this with some type of water or an oil tank or something like that. Okay, so let's talk about emptying an oil tank. So a spherical tank of radius 8 feet is half full, okay, that's important to note, half full of oil that weighs 50 pounds per cubic foot. All right, find the work required to pump all the oil through a hole in the top of the tank. All right, so kind of just set this up. Here's what I have. I have this tank like this. All right, and it has all this fluid in it. And what I'm going to do is I'm going to push the fluid up and out the tank. All right, so consider the oil to be subdivided into discs of thickness delta y and radius x. So this is going to be, as you can see, because I'm doing delta y here, this is going to be a dy problem when I get it, okay? So you can see what's going on here. Okay, so the radius here of the oil in it goes from 0 to 8. That's the radius. And the height of the tank, okay, that the water is getting pushed out is 16 minus y. Okay, because so like what I'm saying here is if you're at 15 feet and you're only going to get pushed 1 more feet, that would be the distance of 1 that you would need to push the fluid out. Okay. All right, because the increment of force in each disc is given by its weight, we have the delta, the change in force, is equal to the weight of the fluid. Okay, that's how much the change in force you're going to need to do. All right, so what is the weight here? Well, the weight we know is, going back to the problem here, 50 pounds per cubic foot. So it's the weight is equal to 50 pounds per cubic foot times the volume. All right, so, well, we know that this volume here is, or this 50 is here, so what is the volume of a sphere? Well, you just have to look up the formula for that, and it's just pi times x squared times the change in y. All right, because the volume is going to change depending on how much the y is changing. So for a circle, we need to find something here. Notice how we have 2 variables. We have delta y. So just going back, hopefully you can kind of see where this is going. Delta y is going to get replaced by dy in my integration. So I'm going to need something to replace x squared with in terms of y. All right, well, how can we relate x and y? Well, for a circle of radius 8, and that's what's going on here with our cylinders here. Okay, like the top part of this here. Okay, this disc, the top part of the disc is a circle. All right, so for a circle of radius 8, that disc here, and center 0, 8 on that graph that I have, you have the following: x squared plus y minus 8 squared is equal to 8 squared, right? Obviously, this is the same from just the equation of a circle. So when you simplify this, it ends up just being x squared is equal to 16y minus y squared when you go through all this. All right, and what you can do is you can write the force increment as the following. Delta F, change in F, is equal to 50 times pi. Now look, I can replace x squared, boom, with 16y minus y squared times dy. Or excuse me, delta y. So now what you can do, all right, is you can figure out how to find the work done. Okay, so note the disk at y feet from the bottom of the tank must be moved a distance of 16 minus y feet to get to the top. So the increment of work, all right, so the delta W is equal to the change in force times 16 minus y. So going back in, so force times distance, right? That's what work is, force times distance. So to go back just so you can see, this is my force, and I'm just multiplying it now by the distance. So I just have to do a little bit of algebra here, all right? And when you do a little bit of algebra, this is what you get, all right? I'm not going to waste time going through it because I know you can all do this. So now what we have to do, because the tank is half full, all right, y ranges from 0 to 8. You wouldn't do 0 to 16. And the work required to empty the tank, W is equal to the integral from 0 to 8, that 50 pi, and then times that algebraic expression we had. And remember, delta y gets replaced by dy. Going through, you can do this integration very easily. Plugging these values in, you just get the following, which ends up being roughly 589,782 foot-pounds of work to push this liquid out. All right, so to estimate the reasonableness of this result, right, consider that the weight of the oil tank is roughly, going through just looking at this, 53,616.5 pounds. So lifting an entire half tank of oil, 8 feet, would involve a work, and this is just done by constant. You can see just using the work is equal to force times distance. roughly 428,000. All right, but because the oil is actually lifted between 8 and 16 feet, right, it seems reasonable that the work done is about 589,000 foot-pounds. All right, class. I know this stuff is difficult here, but if you just follow the formulas, you'll be able to get this when you go through your homework this week. Thanks, class.